Hello there, Mr. Sutton here, bringing you the Pre-Cal Honors 4-1 Part 2 homework solutions on exponential functions with a special focus on using the HalfLife formula. On this problem, we have a PowerPoint file that takes 6% longer to save every 8 days. If it initially takes 5 seconds to save, how long will it take after 283 days? So since this 6% increase in time only happens every 8 days and not every single day, we're going to use our HalfLife formula, AB to the T over K. Going through and filling in some of these values now, the A value, the initial value, is 5 because it's 5 seconds initially. And then the B value, what we're multiplying by every so often, well, it's going up 6% each time, so that's going to be 1.06 for the B value. And then we're going to have T over the K value of 8, because we want to wait until we get to 8 days before multiplying by a full 1.06. So here's everything in place. Now we want to know how long this file is going to take to save after 283 days. So we'll plug 283 in for T. And now we need the calculator. So we have 5 times 1.06 exponent 283 divided by 8. And if you have one of the newer calculators, you don't need a parentheses around the exponent if you have the superscript. So that should come out to 39.279-ish seconds to save. And I'll just round that off to 39.3 seconds. On this problem, the cost of a swimsuit is increasing by 8% a year. Cost today is $35. We want the cost in 10 years. So since this is happening every single year, we're just going to use our standard exponential model here, AB to the T. And our A value, the initial value, is the $35. B value, we're increasing by 8%, so we're multiplying by 1.08. And then we'll just write that out, and then we'll plug in the T value in a minute. So we've got 35 times 1.08 to the T. Now we want to know the value in 10 years, so plugging in 10 for T, 10 for the exponent. Let's use the calculator for the rest of this. So here we go. I've plugged in everything in the calculator. And that's going to come out to, wow, $75.56 approximately. On this problem, a population of mutant alien butterflies multiplies at a rate of 235% every 142 minutes. Wow, we're going to be overrun in no time. What will an initial population of 300 butterflies grow to in 10 hours? All right, so this one has many levels of trickiness. First level here is, since this growth rate is happening every 142 minutes, thankfully not every single minute, we're going to need our HalfLife looking formula. So AB to the T over K, we need that fractional exponent because this is not happening every single minute. So for our A value, we're starting with 300 butterflies. B value, what are we multiplying by? So if I'm increasing 235%, I have to remember, add this to 100% and then move the decimal. So this is actually going to be 335% that we're multiplying by, or 3.35. And then I'm going to have T over 142, because it's 142 minutes we have to wait. So putting everything together, we have our initial value. This is our growth factor. Again, 1 plus this percentage, and then T over 142 minutes. Now the other tricky part about this, we wanted to know what this is growing to in 10 hours. The formula here is written in terms of minutes. This is 142 minutes, but we're plugging in 10 hours. So we need to convert this to minutes. 10 hours is really 600 minutes, so we're really doing F of 600 here. And let's use the calculator for this now. So here's everything entered, and this is probably going to be a very large number. And it is. So this comes out to 49,615.9, or actually, let's round that up, 616. And that's going to be mutant butterflies. On this problem, in 1985, there were 285 cell phone subscribers in Centerville. The number of subscribers increased 75% per year after 85. We want to know how many subscribers were there in 94. All right, so because we're only increasing every year, we can just use our standard exponential model, AB to the T. We started with 285 for our A value. For our B value, we're multiplying by 1.75 every single year, because this is a 75% increase. And we'll just write that out for now. So 285 times 1.75 to the t. Now, what's the t value going to be? Well, the number of years between 85 and 94, that's going to be 9 years. So we're plugging in 9 for t. And let's use the calculator for this. So we've got everything plugged in, and that's going to come out to 43,872 if we round off. Presumably, we can't have a fraction of a cell phone subscriber. So there we go. For number 5, the half-life of midtermium is 4 weeks. If 48 kilograms are present now, how much will be present in 31 weeks? So because we have one of these half-life sort of problems, we want to use the half-life formula. So that'll be f of t equals ab to the t over k. And we want to use this because we're multiplying by 1/2 only every so often, not every week. We're doing it every 4 weeks. So plugging in some values here, we have a start value of 48 kilograms. The growth factor, it's half-life, so we're multiplying by 0.5. T will plug in later. For k, though, this is how long we have to wait before multiplying by 0.5, and that is a value of 4 weeks. So we'll just use 4, and remember that this is in weeks. So we have 48 times 1/2 to the t over 4. Now for t, we want to know about 31 weeks. So we'll plug in 31 for t, and now we'll let the calculator figure it out. So on my calculator, I do my little superscript exponent thing, and it automatically knows that 31 and 4 go together. If you have an older calculator, you might need to put a parentheses around this 31 divided by 4 to make sure that it happens before you use it as an exponent. Pressing enter now, you should get an answer of about 0.2 if we round it to the nearest tenth of a kilogram. For number 6, we've got a half-life problem dealing with carbon-14. Here's our half-life of 5730 years. 12 kilograms present now. How much present in 8,000 years? Let's use our half-life formula, AB to the T over K. A is our starting amount of 12 kilograms. B is 1/2, since we're talking about half-life. T will fill in a minute. K is the time we have to wait before multiplying by 1/2. So 5,730 years. And now that we've got this set up, we have a t value of 8,000 years, which I will now put in my calculator. So if your calculator does superscript exponents, then you're probably good here. Otherwise, you can put 8,000 over this in a parentheses. Pressing enter should end up with about 4.6 kilograms of carbon-14. On this problem, this is a fairly standard half-life kind of problem, literally talking about half-life of plutonium. So that's going to be 24,065 years. If 80 kilograms is present now, how much is present in 14,000 years? So the half-life here is a big tip-off. We need the half-life formula. Our starting value, our A value, is 80 kilograms. The B value, we're multiplying by 1/2 because it's half-life. This is the amount of time it takes to multiply by 1/2. So we're going to do T over 24,065. And this is our initial setup then. Now we have to find out the t value we're plugging in. We wanted to know the amount left after 14,000 years, so that's going to be our t value, 14,000. And now we definitely need the calculator for this. So here's what it looks like with everything plugged in. I've got 80 times parentheses, 1 divided by 2, or 1/2. And then here's my exponent. Press and enter. That's 53.5 kilograms if we round it off. For number 8, we have radioactive iodine, whose half-life is 8.1 days. We're starting with 7 milligrams. We want to know what's left after 5 days. So we're going to use our half-life formula, AB to the T over K. We have a starting A value of 7. B is our half-life of, well, actually it's the 1/2 because this is half-life. K is our half-life of 8.1. That's how long you have to wait before multiplying by 1/2. And T will fill in just a second. So there's kind of our template for all of these. So now we've got a T value of 5 because we want to know what's present after 5 days. And let's plug that in the calculator. And if we've done this correctly and press enter, we should end up with about 4.6 if we round up. So that's milligrams. For number 10, we've got a population growth problem. Some rabbits are tripling every 40 days. If 20 are present now, how many will there be in 365 days? So because we're tripling every so often, not every single day, we're going to use our half-life formula. So AB to the T over K. We have a starting A value of 20 rabbits. The B value, this is what you're doing each time, which is tripling. So we're multiplying by 3. And T will fill in a sec. The K value, that's how long we have to wait before tripling, and that is a value of 40. So we have 20 times 3 to the T over 40 as our starting point. And now for the T value, we wanted the number of rabbits after 365 days. So that's our T value, 365. Let's plug it in the calculator and see what happens. So we've got 20 times 3 to the 365 over 40, which comes out to 451,607.8. So we'll round that up to probably 608 rabbits. I don't think we want a fraction of a rabbit.